Welcome back to another domain video. So in this case, we're going to solve more complicated rational expressions and perhaps some radicals too. So the first one is 2x plus 1, and then we're going to have that divided by, let's see, how about x squared plus 2x minus 35. Well, we have a fraction, so if that's the case, the denominator cannot equal to 0. Last time, in my previous video, we had a difference of two squares. We could use a factoring formula or the square root property. In this case, we have to use standard factoring. So factors of negative 35 that add to 2. Well, I could have a positive 7 times a negative 5. That gives me negative 35. Likewise, 7 minus 5 would give me 2. Now I set each factor equal to 0. Upon subtracting 7 to both sides, we get x cannot equal to negative 7. Or for this next factor, we could add 5 to both sides. So x cannot equal 5. So these are my restricted values. Therefore, my domain consists of all numbers on the number line, excluding my restricted values of negative 7 and 5. So I graph all numbers on the number line except those two. Well, that gives a great visual interpretation, but how would I express this in interval notation? Well, from negative infinity to negative 7, also the shaded region between those two numbers, negative 7 to 5, also 5 to infinity. Now, last time we didn't do an example containing a radical, so let's see what that looks like. Suppose we had a function defined as the square root of 12 plus 4x. Well, the rule was the radicand, the expression under the radical, must be greater than or equal to 0. So again, every time you have a radical, you use this inequality symbol. Whenever you have a denominator, we used this symbol. So in this case, I would subtract 12 to both sides. Then dividing both sides by 4 gives x greater than or equal to negative 3. So the function is defined for all values of x equal to negative 3 and greater than. So in interval notation, this would be bracket negative 3 to infinity. So notice now we're introducing this different inequality symbol. Again, if it's a radical, it does contain an equal sign. Because this contains an equal sign, we're using a filled in circle, a solid point here, instead of an open circle. And yes, the open circle meant we had a parenthesis, whereas the filled in dot means we have a bracket. What if you had this g of x is the fourth root of 7 minus 8x? Well, I would take the number under the radical which is 7 minus 8x. Again, if I have a radical, I use this inequality symbol. I would subtract 7 to both sides, leaving 8x greater than or equal to negative 7. Now here you're dividing both sides by a negative. When you divide both sides by a negative, or multiply both sides by a negative, the inequality symbol reverses its direction. So here we have all numbers on the number line except 7 over 8. So I can be equal to 7 over 8, or x is less than. So when I read this blue graph from left to right, I have negative infinity to 7 over 8, filled in circle is a bracket. Now, here's more complicated examples that I'd like to do where, yeah, there's just some technicalities. So what if we had, here's a tricky example. What if we combined the two scenarios? What if we had a rational expression which also contains a radical? Well, actually, by definition, that wouldn't be a rational. Let me speak precisely. A rational expression should be a ratio of two polynomials. Well, whatever this is, it's going to be a mess. It's a fraction, but it's not a rational expression. Okay, so here we have a radical. So 6x minus 11 must be greater than or equal to 0. But simultaneously, it's also a denominator. And if it's a denominator, well, the denominator cannot equal to 0. This suggests that our equal to sign here will no longer exist, leaving it as greater than 0. Now we solve. Dividing both sides by 6, we get x greater than 11 over 6. So when we plot this on the number line, we will use an open circle, since the inequality symbol no longer contains that equal to sign. And again, I'm going to shade all values of x on the number line greater than my fraction. So that's what it would appear as. So that's a combination of having a denominator and a radical. But yeah, we almost covered an example of each type of problem. But now what if the radical was in the numerator? Because notice how this allows us to ignore the numerator entirely. There's no restrictions on it. It's a polynomial. So the last scenario would be you have the square root of 2x plus 5 divided by x squared minus 9x minus 10. So I'm going to look at the radical. It must be greater than or equal to 0. And the denominator cannot equal to 0. Now we solve both individually. Subtracting 5 to both sides. Dividing both sides by 2. We're left with negative 5 over 2. Now for our polynomial, we need to factor it. Factors of negative 10. Well, how about, -10, and +1. Because they multiply to give -10, they add together to give -9. I set each one equal to 0 individually, or in this case, not equal to 0. So x would be not equal to 10, or x is not equal to -1. So we graph these restrictions on the number line. So we have a -5/2, a -1, and a 10. So let's shade these one by one. So the first case is I could be equal to -5/2 and all numbers greater than. Let's look at the next restriction. X cannot be 10. So it could be all numbers on the number line except 10. And the last restriction, x cannot equal to -1. So here, let's put the circle there. So x can be all numbers except -1. Now, how do we format the final answer? Well, that's where all graphs, all shaded regions overlap. So I do have my orange and my green here overlapping, but I also need the pink to overlap. So I'm going to shade each region, each interval that has orange, pink, and green. So that's from, I'm just going to write down at the very bottom, from -5/2 to -1. Then all of them overlap from -1 to 10. And then the orange, the pink, and the green graphs overlap from this interval, from 10 to infinity. 10 to infinity. So that's what the final answer would look like.